Welcome back to this afternoon session. So the next speaker is Lorenzo Baldi, and he will explain how to obtain polynomial degree bounds for Polynomial applications.
Thank you, Victor, for the introduction. I'm very happy to be here and to do this conference in presence. And okay, let's start like everyone here, recalling the basic of polynomial optimization, just to fix the notations that I will use in the talk. So we have our objective function, which I call h, which is a polynomial in n variables, and we have the inequalities g1, gs, which are again polynomial in n variables. The inequalities define the basic closed symmetry of x at S, so the point x in R to the S such that gi of x is greater or equal than 0. And the goal of polynomial optimization is to find ways to compute the infimum h star of h on the basic closed symmetry of x at S. And this is a difficult problem, NP-hard problem, and we have to find ways to compute approximation of this. And the way to do that is to notice that h star can be written as the subminimum for lambda and r such that h minus lambda is a non-negative polynomial on S. And so what we want to do is to find inner tractable approximation of the convex cone of non-negative polynomials. And in this way, we can compute lower approximation of the minimum of h star. And okay, so I denote in the talk sigma squared, the sum of squared polynomials, again, a convex cone containing the globally non-negative polynomials. And I denote QR of G, the truncated quadratic module at degree R. So the polynomials that can be written as sum of squares plus sum of squares times GI, where we bound the degree of every delta by R. And of course, this is a subset of the convex cone of non-negative polynomials on S by definition. And so this gives, for every R, gives a lower approximation of the infimum. So I define the set of original relaxation, sum of square relaxation as well as R as h star sum of square R. This is the subminimum for lambda and R such that h minus lambda belongs to the truncated quadratic module at degree 2R. So replace positive polynomials by truncated quadratic modules, and we get a lower approximation. Since we can do that for every R, we have a hierarchy of lower approximations that are increasing by definition and always smaller or equal than h star. And every relaxation is a semi-definite program. You know better than I do, of course. And the important thing is that if the quadratic module is Archimedean, so this means that a ball constraint belongs to the quadratic module, then we have convergence of these lower approximations to the minimum h star as the order of the approximation R goes to infinity. And the question that you want to investigate is the following. What is the rate of convergence of this lower approximation to h star? And this question can be restated as follows. We have to go through the proof of this convergence. So we notice that for all epsilon strictly bigger than 0, then h minus h star plus epsilon is strictly positive on the symmetry of x at S. And Putinar's positive tells us that this strictly positive polynomial belongs to the quadratic module. But notice that the degree that we need to represent these strictly positive polynomials depend on this epsilon that we have. And so, if we have R such that h minus h star plus epsilon belongs to the truncated quadratic module at degree 2R, then the error that we have at order R of the hierarchy is smaller or equal than epsilon. And so, the answer to our question to compute the rate of convergence is to analyze the dependence of this R on epsilon. Okay. Again, we have these equivalent questions, the rate of convergence of the lower approximation to h star. This can be restated as as follows. What is the quality of approximation of the convex cone of non-negative polynomials by truncated quadratic modules? Or even more explicitly, and this is the way we will discuss in this talk mostly, if we have a strictly positive polynomial f on S, then f belongs to the truncated quadratic module for which at which degree R we need to represent this polynomial. Now, sorry for this part, we have a wall of notations, but they are important and we have to remember them. So we have f, which is our polynomial, it will always be strictly positive on S. We denote d or df, the degree of f, and dg, we denote the maximum degree of the gi. And now, the most important thing, you just need to remember that epsilon of f is a measure. We denote epsilon of f a measure of how close is f to have a zero on the symmetry of S. And formally, it is defined as follows. It is defined to be f star, so the minimum of f on S, divided by the norm of f. I will not explain which norm we use. It's all of them are equivalent, and it's important a choice, but let's ignore this problem. So epsilon of f measures how close is f to have a zero on S, and it is f star divided by norm of f. And we will need also some geometric properties of the G, of the inequalities. Let me stress this point, it's important. These are not properties of S. These are properties of the G. The description of the semi-algebraic set matters. It's not the semi-algebraic set, is the description.
Sorry, do your result depend on the norm?
No.
No.
No, I mean, we are using a norm which is asymptotic. Okay, of course, the precise bound, yes, but the asymptotic of the bound does not depend on the norm. What we do in practice is to choose a max norm because it's easier to deal with, but you could use other Weil norm or very Weil norm, something other things, of course, or a Euclidean norm of the coefficients. Okay. So
I didn't quite understand your comment that it depends on the properties of G.
okay, so there is let me say this. In the univariate case, there is a if you have a segment here and you describe the segment, for instance, in the natural way, it's the segment minus 1, 1, you describe it like 1 minus x squared, you don't have any problem because you know that if f is strict, there is no negative, non-negative on minus 1, 1. Then you have a representation which does not that does not depend on f, so it's constant. Okay?
Yeah, but that's the univariate.
If you describe things like that,
clearly,
then this is going to change, and you need you have the degree goes to infinity. In the multivariate case, you always need the degree to go to infinity. But if you describe the semi-algebraic set in a bad way, you may need a higher order.
Yeah, that's my question. So I worked a lot on the univariate case to find these natural generators that will always make the preordering saturated. But in the multivariate case, what would be the proposal?
I will explain this in talk, and maybe we have. Okay, so let me review some literature on the representation of positive polynomials on special semi-algebraic sets and on general semi-algebraic sets. Most of the authors are in the audience, so if I say something wrong, please correct me. So let me recall again Puttiner's positive spelling sets. So if we have an Archimedean quadratic module and f is strictly positive, then we can represent f in the truncated quadratic module for some degree r. Okay. Let me recall also Smoot-Game positive spelling sets that was just mentioned. If we denote G capital I, the product of for I in I of the GI, we define the truncated preordering. So here we allow not only the generators of G, but also their products as some of these addenda. And Smoot-Game positive spelling sets tell us that if the semi-algebraic set S is compact and F is strictly positive, then F belongs to the preordering of the G. Okay, this is just to fix the notations, and this is what I wanted to say. Let's recall some results on special semi-algebraic sets. We have our F, which is strictly bigger than 0, and I will omit a lot of details, so don't take this slide purposely, look at the papers. If we take the semi-algebraic set S to be the n-dimensional sphere, then we have F that can be represented in the quadratic module of the sphere, which is also the preordering of the sphere, and the dependence of R is big O of a constant C that depends on the degree and on n times epsilon of f to the minus power minus 1 over 2. And this is a very good convergence that was proven by Punk and Fauzi. And okay, on the same line, using polynomial kernels, Monique and Lucas extended this technique to other symmetric sets. For instance, if you take minus 1, 1 to the n, then f belongs to the preordering defining minus the natural preordering defining minus 1, 1 to the n, and the dependence is again epsilon of f to the power minus 1 over 2. And okay, again, if we have the unit ball, we have a similar dependence here. Let me mention another result, which is Polya's theorem, effective version of Polya's theorem proved by Power and Resnick. And here they prove a dependence on epsilon of f, which is the power minus 1. So in principle, it's a worse dependence than this one. This result seems better. But for our application, the fact that the dependence on D is this square make these results more interesting than these other results, which are D to the power n over 2 in some sense. So not only epsilon of x is important, but can be important also the other constants. And okay, now let's move to general symmetric sets. If this is a version of Smooth positive spelling set proved by Marcus. And if the symmetric set S is compact, then we have a dependence on the degree R, which goes like epsilon of x to the power minus C for some C. And notice that this is very similar to these results. Just this C is unknown can be very big. So this gives low convergence. We don't know the C. But the thing is, when we move to Polynomial positive spelling sets and we have a quadratic module, which is Archimedean, then the dependence that was proven initially by me and Marcus is exponential in epsilon of f to the minus. And was an open question whether it was possible to kill this exponential. And this is the main topic of the talk. We kill this exponential and get a dependence for the Polynomial positive spelling sets, which is similar to Smooth positive spelling sets. Let me mention also these are the recent results, which is a version of Putin and Vasilevsky theorem proven by Mai and Victor. And they proved that they have a dependence which is without this exponential for R, but they need to multiply f by a sum of square multiplier. Okay, so here is again the theorem of Ni in more details. We need a normalization assumption. So we need S of G to be inside the unit box. And we have this exponential dependence on epsilon of f to the minus C. And this gives, as a corollary, a logarithmic general convergence of the log approximation to H star. So we have a logarithmic convergence of our log approximation to H star. And what we want to do is to prove a new bound, which is polynomial in epsilon of f to the minus 1. And moreover, answering partially what Salma just asked, we want explicit constant and exponents. We want geometrical properties to appear explicitly. Okay, let me present immediately the main result. Under more or less the same assumption of Marcus, we assume that the quadratic module is Archimedean and that the bone constraint with the radius 1 appears explicitly, it's not a problem. Then we have a dependence of R on epsilon of f, which is of the same type of the smooth one. So epsilon of f to the power minus 7 times the log-adjacent exponent plus 3. And okay, this is the final result, and it illustrates polynomial dependence, which is what we wanted. And the parameters are very explicit. N is the number of variables, S is the number of inequalities, D is the degree of f that we are representing. And now the only mysterious two are these CE and LE. These are the Lojasiewicz constant and exponent that I will introduce after, and depends on the properties of the G. But let me give first an idea of the proof. So we fix D, which contain S, to be a compact semi-algebraic set for which we know some good positive Steller sets. I have listed them before, so we could take D to be the unit simplex, we could take the unit ball, we could take the hypercube. Okay, what we want to do, we want to deform f, which is, we know it is strictly positive on S, we deform it to be strictly positive on D using some Q, and this deformation Q needs to be in the truncated quadratic model. Once that we do that, it's not working. Okay. If we do that, from the Archimedean property, we know that the preordering of this special symmetric set that we have chosen is a subset of the quadratic module. You can look at this expression that gives this result. And once that you have this, it's done, because then F can be written as P plus Q. P belongs to the quadratic module, Q belongs to the quadratic module, and we have the representation that we want. So looks easy. What is the problem then is the construction of Q, of the deformation polynomial. And we want this in such a way F minus Q is strictly positive on the bigger set D. This Q, we need also to determine which is the degree that is needed to represent it. And this degree depends on F and G, and more specifically, will depend on these geometric properties. So what is the idea here? Maybe, I don't know if you see here, but let's say that this is D, this is S. F is strictly positive here, and can be, I don't know, here can be negative. So when F is already strictly positive, we don't want to take off many things. We want Q of X to be small here. On the other hand, if F is negative here, we need Q to contribute positive. So minus Q to contribute positively, and so minus Q should be big. So we want something which is small here and big here. Okay, it's rather natural. And now, if we forget about polynomials for a second, this is rather clear, right? Because we look only at continuous functions and define A here. So we define A here, and A is defined to be, it is the joint from S, and it is the set where f of x is smaller or equal than a fraction of x star. This A is by definition disjoint from S. And since these two sets are disjoint, we can apply Euler's lemma and find a continuous function that makes our inequalities true. Now we are also in a metric space, so we have also explicit expression for this. It's not really important, but the thing is, naturally, if we look at continuous functions, we can find it easily. And so what we want to do is simply to find an approximation of this. We know that polynomials are dense, and so these perturbation polynomials should exist. Okay. Now this is not working. Okay. And now answering Salma's question, what do we want to do? We want to compare F and Q on the symmetric set S, or sorry, on D, not on S. We want to compare F and Q on D. And to do that, we define two functions. Capital of F of X, which is defined to be the absolute value of the minimum between F of X minus S star and 0. And this describes how F vary outside of S, in some sense. And then we define G of X, which is what we call the symmetric distance. So this is the absolute value of the minimum between G1 of X, GR of X, and 0. Then everything is normalized for simplicity. This function we call symmetric distance. It's known as also as residual function in the theory of error bounds in polynomial optimization. And it is telling you how the inequalities vary outside of S in some sense, geometrically. And now, since the zero locus of G and the zero locus of F are, this is included in the second, we can apply Lorentzian inequality, and there exists a constant that depends on F, of course, and G, and the exponent such that the first F, the F of X to the power LF minus is more or equal than the constant times the second function at S. Now, you see how natural it is to use a function F that depends on small f. So this exponent here depends on the objective function. This is not something that we want, or at least we don't want at the end. And to prevent this problem, we can factor this inequality. So we introduce as intermediate step the Euclidean distance function from the semi-algebraic set S. This is a continuous semi-algebraic function. And so we can apply again Logiciel's inequality. On one side, we need to compare f with E, with the distance. So in some sense, how f vary and the distance. So this is something like estimation of the Lipschitz constant. And they goes under the name of Markov inequality. And so we have a Markov inequality, f of x is more or equal than constant that depends on the degree and on the domain that we choose times the Euclidean distance. And then we can use a Logiciel inequality this time between the Euclidean distance and G. And then we have associated exponents CE and LE. And now using these two inequality, you can get rid of the dependence of f. But in general, we will see that it's more natural to use this one in some sense. Okay, now again, what are we doing? What are these Logiciel exponent and constant? This is our semi-algebraic set S. We have two polynomials. G1 is a cubic, and we have a ball. And we want to compare these functions with the level sets of the objective function. So these are the level sets of our objective function, and I have chosen a smooth objective function, and so the level sets are very regular. Nice. What happens if I compare these level sets with the level sets of the inequalities? Okay, if I take the ball, nothing strange. This is perfectly smooth. So we see that the variation of these goes a constant time the distance, the variation of these goes like a constant time the distance. So the Logiciel exponent, if we consider only these two, is 1. But what happens if I consider the singular one? We see that the level sets of the singular equation have this strange behavior. And in this case, the Logiciel exponent will be something like 3/2. And so this is the geometric content of the Logiciel exponent. The geometric content of the constant is more complicated and not well studied in the literature. We have some estimates for the constant in some regular cases. Okay, now we have all the geometric ingredients. We just want to construct our Q. Q in the quadratic module such that f minus Q is strictly positive on D. And what is the idea? So here we want f minus q, f is already positive, we want q to be small. What is the point here? When we are inside the semi-algebraic set S, all the inequalities are positive. And when we are outside, there exists at least one inequality which is negative. So we consider this function, which is again not a polynomial. I call it phi, and we consider phi of x, which is the composition of phi with gi. And what happens? Let's see what happens. If I take a point inside, then gi is positive, and phi of gi is more. On the other hand, if I am outside, this is I can choose the one which is negative, gi, and this is big, as we wanted. Okay? And so what I do is to consider an approximation. This is not a polynomial, of course. Again, I consider an approximation. This is what I want to do. I consider an approximation of this, or I consider an approximation of phi of x, and then I define q to be the sum of sigma I, that are this our approximation, times gi. And we can prove that this q works. Now, where is the geometry that I have explained before in this expression? It is on the dependence of k. K is the degree that we need, and depends on what is the degree needed to approximate this function, more or less. And so the worse is the geometry, the smaller this step will be. And so this function will be steeper and steeper, and so it will be harder to approximate. You will need higher degree polynomials. So the worse is the Logiciel exponent and constant, the higher the degree you need to approximate this function, the higher the degree will be in the effective Polynomial sets. And okay.
When you say geometry, which geometry do you mean? Of the semi-algebraic set?
This geometry.
The geometry of the semi-algebraic set or not?
The geometry of the level sets of the inequalities, of the defining inequalities. I mean, if you, in this case, even if it is small, if it is smooth, you can replace the smooth polynomial that defines this, add something which is useless, and you will get some perturbation of the level sets, and so the exponent will be worse. Okay, again, here is the result. It's not the result I explained before. It's the result with LF, with the exponent that depends on F. And this is, okay, this result is not giving us the general convergence that what I wanted before, but philosophically it's the correct things to think about, because you see, it was not necessary to factor to the distance. And this gives, in principle, better bounds than the one that you have when you consider the distance in the middle. And it has application or potential applications. For instance, if you want to compare quadratic modular preorderings, consider the simple case of 0, 1 to the n, defined in one natural way. There are several ways, of course. Then we know that the product of the xi belongs to the preordering, but the product of the xi does not belong to the quadratic module. On the other hand, by putting us for this Spelling-Satz, we know that the product of the xi plus epsilon belongs to the quadratic module. So in some sense, comparing the preordering and the quadratic module reduce to find the degree that you need to represent this polynomial. And so it is a question to find the smallest epsilon such that the product of xi plus epsilon belongs to some fixed order. And the conjecture by Monique and Etienne was about the degree n level of the truncated quadratic module, and they conjecture that you can take it, the minimum epsilon that you can take is 1 divided by n plus 2. And so if you want to tackle these problems, you don't want to have the dependence on the Euclidean distance. You just want to have, it's okay to have the dependence on the Lojasiewicz on the small f also here, because this will give better bounds. If you consider the worst case scenario when you use Markov inequality, you may lose a lot. While in these concrete cases, it's better if you have the dependence more explicit. And in general, okay, this result is very general, of course, cannot be used in a reasonable way for this case. But in general, if you want to compare Sputin and Smutin hierarchies, you may want to use a result like that. And I asked the author of the other result that I presented before, maybe it's worth presenting the next positive Spelling-Satz using this philosophy as well. Not only the worst case, but also this special one. And okay, this is the result that I presented before. So this result is the one with Lojasiewicz exponent that does not depend on f, but you see there is this d to the 14 LE appearing, which is the worst case scenario, and we are not really always looking at it, but these results can be used to prove as a corollary, the polynomial convergence of Lasserre hierarchies. So here we have, in this theorem, we have explicit constant exponents, we have the polynomial bound. In the worst, we have worst case estimates due to Kurdyk and Podrieja for the Lojasiewicz exponent. And finally, we have our polynomial convergence of the lower approximation to H star, since this dependence is polynomial, as we want. Sorry. Oh, yeah, okay. So, thank you. Okay. As I said before, there is a huge analysis in the real algebraic geometry literature on the Lojasiewicz exponent. The constant is much less understood, and most of the things are done for the worst case scenario. So coming back to this slide, there are these kind of results tells you, okay, in the worst case, we have these things. These are not typical conditions in optimization. In optimization, you have usually regular things, the equations that you choose are the best possible. And so we try to analyze this case in the regular case, and what does it mean in regular case? So first, we need to define active constraints at a point x of the semi-algebraic set S, and these are the GI such that GI of X is equal to 0. And we say we are in a regular situation when the constraint qualification condition holds. And this means that the active constraints at all the points of the same algebraic set S as linear independent gradients. So this is not the case. Here, the gradient of the only active constraint, which is the cubic, is 0. So this we are not in this situation. But if we are in a box, we are in this case. If we have a ball, we are in this case. Okay. And in this case, we can prove that the Lojasiewicz exponent is equal to 1. So, as we expected, and we have estimates for the Lojasiewicz constant, and these estimates depend on essentially on the condition number of the system of inequalities. The closer these inequalities are to have a singular point, the bigger this constant will be. I will not enter the details, but this is the idea. And there is a local and global analysis to do. And we discovered just recently that this was already known only in the convex case, and you can find it in the survey of Pang in the 97, and it is a result of Lee in the 84th. And this is due to this again the theory of residual functions that I was not aware of since 1 month, well, till 1 month ago. And so the Lojasiewicz exponent is 1, and we have estimate for the C, and we can plug in these things in the previous result. So if we have constraint qualification condition at every point of this algebraic set S, then we can take we can see that the Lojasiewicz exponent is 1, and we have this estimate for the constant. Okay. Let me conclude briefly, recalling the dual perspective. So we have seen how the Putinas positive Stellensatz, the effective Putinas positive Stellensatz, is a quantitative polynomial approximation result of non-negative polynomials. And so QR of G is an inner approximation of non-negative polynomials. What happens if we take the dual? So from Aviland's theorem, the dual cone of the non-negative polynomials, so the linear functionals acting on polynomials such that lambda of f is greater or equal than 0 for every non-negative polynomial. This is by Aviland's theorem equal to the, well, equal. If we identify the measures with their moments, if we identify measures with the linear function that they induce on polynomials, then this is equal to the convex cone of Borel measures supported on the same algebraic set S. And now we can dualize also our truncated quadratic modules, and we get the truncated positive linear functionals or truncated positive pseudo-moment sequences. And these are the feasible pseudo-moment sequences of the Lasserre moment hierarchy. And so the dual question of the Putinas positive Stellensatz is, what is the quantitative approximation of the convex cone of Borel measure by truncated positive pseudo-moment sequences, or equivalently, how close are these feasible pseudo-moment sequences of the moment relaxation to be moments of measures? And the results, I will not give degree bounds, I will not explain the details, but the thing is that you can obtain the dual result from the effective Putinas positive Stellensatz. So we can bound the Hausdorff distance between our truncated cones of positive pseudo-moment sequences, the Hausdorff distance between this cone and the Borel measures. Okay, so this is the conclusion. Just to take the take-home messages. So the positive Stellensatz, what we use Lojasiewicz inequalities and polynomial approximation, nothing more. And we prove that polynomial rate of convergence, and then we have a polynomial convergence, general polynomial convergence of Lasserre hierarchies. And let me mention some perspectives for the proof. We are not really using sum of square polynomials. We are really using approximation. So this on one side is strange. Maybe for sum of square polynomials we can do much better. And on the other hand, it's good because it opened the line to other questions, maybe to other directions. So maybe we can use this approximation for splines with the song, or using some linear approximation of the cone of positive polynomials. There are some works of the people in Tilburg by Lorenz and authors that are dealing with different cones that are not the sum of square cone and proving positive spell results on this direction. We conjecture that the best possible exponent that we can get is a constant times L minus 1. And this would be coherent with the result of Marshall and me that tells us that generically we have finite convergence of the sum of square hierarchy. And finally, we would like to express our result in some concrete examples. For instance, I mentioned before the case of the hypercube. We would like to have good bounds for the quadratic modulus on the hypercube, maybe using similar techniques, or maybe there are some things to do for the volume computation. And okay, finally, we have proven that if we have a regular problem, then the exponent is 1. We are asking ourselves if the convex is 2. In the case of convex inequalities, it's true. It is proven in the paper of Pang. But we didn't try to prove the converse also in our case. And finally, these results could be used also to certificate emptiness of symmetry-like sets, maybe in the rational case and depending expressing the bound on the bit with a dependence on the bit size of the input polynomials. Okay, so this is the end of the presentation. Here you can find the references, and thank you for your attention.
Many thanks, Lorenzo. Any questions for
Yes. So in the case the exponent is 1, so when your constraints are qualified,
yeah,
could you refine then your analysis for the convergence rate, or you just plug the value 1?
No, we didn't try. I think we could. I don't know. Probably. We just plugged in for the moment. We just said, okay, L equal to 1, and I don't know if which part would simplify. I don't know. We didn't try, but it's interesting. Probably the most interesting result for optimization would be in this direction.
Any other questions? Also, online people, I'm sorry I forgot you during the previous talk, but if you have any questions, you can ask.
Is there anything, I mean, if you were to apply maybe not really an interesting case, but has anything you can ever apply to the Boolean hypercube?
The Boolean hypercube is you have just finite convergence always, right?
That's right, but no, I understand that, but can you say something about the because you want to know, it depends on n, and you want to know when can it lead to anything interesting in that case?
We did not do anything, but this would be more. I think it would be more on. Well, okay, we have some results if on the degree that you need for finite convergence of the moment relaxation, not on the sum of square relaxation. But if you define things properly, you have strong duality, and so we have results that are much more algebraic. So, well, and no, our results are not on the finite convergence, are on flat rotation. So, finite convergence of the sum of square hierarchy is another thing that we did not investigate, but we can maybe discuss it later.
Maybe only a small remark about this epsilon n, the conjecture for Monique and
yeah.
Chen. So I looked at it with Monique 1 year ago or something, and then I looked at so I implemented the symmetry reduction, and for n is 10, a slightly smaller value also worked.
Smaller.
Yeah.
Okay, so this proves. Sorry.
Yeah. But yeah,
Sorry.
so 1 over n plus 2 it worked. But yeah.
But you have approximate expression, or you have rush? I mean, you have really
Approximate numerical.
Okay. We are with Lucas. We are going in this direction as well.
going, you mean proving the.
No, not proving, but giving giving estimates.
Yes, yes.
Giving estimates. In this, more precisely in this direction. On the bound for Putinar index median case for the hypercube. This would be the thing, right?
Yeah.
Or explicitly for this very specific polynomial, maybe you can do something.
All right. There is no more questions. Let's thank again Lorenzo.